Anyway, we're recording now. And I'll send you the recording as soon as we're done. Now, so we're starting off with this data. Now, each of you started from the 0 mark. You moved 10 meters up the slope and then took the angle again, another 10 meters up the slope and took the angle again, and so on and so forth. In reality, what you would have done is something like this. So try and get the code to work. And of course, I should share my screen because like this, you're not seeing anything. Right. Why do I have function classification stability here? Yeah, all right. Now, some of you might be able to follow this on your laptops. For those of you following it on your screen, I'll try and enlarge it somewhat. Now, I'm going to render the document first so you get an idea of what we need to produce. Now it says execution halted, which means we're not killing him. So, let's just import the file first. Import dataset from text base. Bless you. Okay, now, if you look at the picture over here, please. When we draw a picture of the slope, that is what we should get. Something like that. That is the slope of the shoreline seen as a shore profile. And that should be part of your site description. Now, the distances that you would have moved from 0 are not in this direction, but in that direction, because you're moving up the slope. Can you see that? And if you decompose that slope, this is actually made up of a lot of small triangles, each of them with 3 vertices. 1, then you drop the right angle and 3. 1 right angle and 3. 1 right angle and 3. Can you see that? It's moving up in steps. And given that we're measuring the length of the hypotenuse, that's 10 meters every time, then what we need to measure, given that we know the hypotenuse because we're walking up the slope and the angle because we've measured it, is the height. Who's Davina? Oh, Kazaya. Oh, your mom joined us. Wow, illustrate. Okay. No, hang on. Okay, all right. It's not like your mom joined us to see what you're doing. And that narrow dynasty, anyway. Anyway, so the thing is that what we actually need to do for each of those triangles is work out the horizontal displacement x, the vertical displacement y, and each time add them up. And that would really give us coordinates on a graph that we can then plot. Now, I'd like you to look at this actual slope and tell me what's wrong with it. Katya, what do you think? It goes up too high. The slope over here is exaggerated. I'll tell you why. Look at the horizontal axis, the x-axis. These few squares are from 0 to 100 meters. But the same distance on the y is from 0 to 9 meters. Can you see this? The slope that we were working on at Alet Marco is not the side of a mountain. It's a shallow slope. So there's another way, as we'll also see, in which to make the slope a bit more boring, perhaps, but that reflects what we had in reality, a gentle slope, that in 100 meters, it only went up by 10 meters rather than by an Everest and a half or something. Are we okay with that, please? All right. Now, we're going to do all of that using GAR, not because it's easier using GAR, but because you learn a heck of a lot more using GAR. And because later on in the real world and in future studies, I assure you, nobody's going to ask you whether you know Excel. Because Excel is great if you're 10 years old, but people will ask you if you can program in R and Shiny and stuff like that. Shiny is just a web interface for R. We could speak about that later on. So we're doing this in this way, not because it's the easiest way, but because it's the way that we learn most from. Is that clear, please? Now, I'm going to use the same codes that I had given to last year's group, and we're going to use them step by step. And later on, you can key in your own data and replace it with that Kim data and whatnot. I'm just going to show you the principles and the codes. And later on, if any of you can come up with simpler codes, be my guest. This code was written in a bit of a hurry, and I'm sure that you can all come up with better codes. You can also do it a different way, something which wasn't available a year ago. You can simply plug all that code into ChatGPT and tell ChatGPT, could you write a simpler, better, cleaner version of this code than the guy at the front bench did? And in 2 seconds, it will give you a cleaner, better version of the code. So that could be something to learn from too. Now, in the first block of data here, I'm going to enlarge this somewhat. In the first block of data here, we're just importing the data itself. Now, if I was writing this now, today, and in less of a hurry, I would add another block that I usually add, which is to delete everything that there is in the memory, just to start from scratch. Is that clear? but I'll do that in the clean version. To cut a long story short, when I'm writing a piece of code like this, I don't know. Yeah, when I'm writing it properly and I've got 10 minutes more, I normally add a few lines like these, you can see here. Basically remove everything, install the packages, and that would be it. I hadn't done that yet. And since then, the Markdown, which I had used a year ago, has now been replaced by Quarto, the thing we had the workshop on last December. So there are a few changes. But in the first block, we're just importing some libraries that we need. ggplot2 is there for drawing graphs. You'll remember it and you'll use it. And the data that we're importing, well, just now it is only valid if you're importing from my own computer. But given that you'll be doing this on your own laptops, then obviously it will have your own username, etc. And the first thing I have here, just so that I wouldn't forget, is the data table. So the distance from the shoreline along the hypotenuse and the slope angle that was measured. If you have that data, that is all you need, because you then just plug it into this formula, yawn a couple of times like Jeremy's doing, and then press enter and off we go. Now, so now I'd like you to look carefully, not so much at the codes, but at the procedure. The first thing that I'm doing here in R is something known as a function. A function is nothing more than a formula. So instead of writing the formula which I need every single time, I simply give a name I can remember to that formula. And instead of writing the formula every time, I just give the name. So I don't know if I want to carry out a calculation to calculate angles in a certain way, I don't have to write the formula each time. I just call the formula, I don't know, Gabriel, and then just write Gabriel. And then it tells me syntax error or something like that. But there's something that we have to start off with. Now, in what units do we measure degrees? Tell me. In what units do we measure angles? And I was just testing you. We measure them using degrees. Now, measuring angles using degrees is, in fact, not terribly intuitive. How many degrees in a circle? How many degrees in a right angle? 90. You notice that although you've known these since you were kids, there's nothing metric about it. You know, why 360 in a circle? Why not 1000? It ultimately all goes back to the ancient Greeks and before those the Babylonians. We've got 12 months because the Babylonians counted in sixes, and their mathematics has come down to us to the Greeks. So because they counted in sixes, we have things in multiples of 6, 12 months, for instance. Remember, the Romans had 10 months, but then screwed up their calendar and added 2 more. That's why December, which actually means 10th month, Decos, is the 12th month. But there you have it. And angles also come in multiples of 6. 360 goes into 6. As you know, 90 goes into 6, etc. Now, that would be great if you're Babylonian, but because very few of us are, and very few of us have even heard of them, then when we're doing proper mathematics, in the sense that when we need levels of precision which are greater, then we actually use the circle ratios themselves. I'm not sure how many of you ever had a pocket calculator. Some of you might have been using their mobiles ever since they were born, but when you've got a pocket calculator, at the top, you've got a little function which is DEG, which stands for degrees. When you press a button, it changes to RAD, radians. When you press another button, it changes to grad. That's because there are two other ways of measuring angles. One of them is in grads, which means that the right angle is 100 degrees and also is 400 degrees. I'm going to be using that. But the most popular way in mathematics and by extension in applications of mathematics like coding is using radians. Now, does anyone know what a radian is, please? Or have you ever heard of them? Great. So let's, Jeremy, you have. Go on. Very good. Now, he mentioned the word pi, and some of you saying it's too early for supper, etc., but it's not that pi. Jeremy is talking about a pi, which is a mathematical constant, which many of you know to be 3.14159265 and keeps on going. Doesn't actually stop. Now, we find that pi in circles. Now, when the Greeks came up with pi, why the hell did they come up with 3.141? Why not just 3? Then, what's pi in English? Radius. If you get the radius of a circle and make it bendy, it fits inside the circumference of a circle, 3.141592654. It's very precise. Whatever the size of the circle. Of course, that number is a bit not enough of a round number for it to anxiety. You know just how advanced the United States of America are. And about a century and a half ago, one of the southern states, I forgot which one it was, actually put it to a vote in their own Congress to change the value of pi to 3, because it's simpler for everyone. And it came within a couple of votes of getting accepted. Of course, not really. Because you can't vote on constant. But the thing is that once we've got this constant pi, then we can actually use it to measure angles with. And as Jeremy was telling everyone, but only England was really listening, then the number of radians and a whole circle, so 360 degrees, is 2 pi radians. So 3.1415926 whatever times 2. Do you understand that? And working with radians is the way that computers work. It's the way that people who work seriously with circles work. Ultimately, when I studied some mathematics beyond 5th form, you then realize that only school children work with radians. Beyond 5th form, everyone works in radians, which obviously gets me to ask the question, why don't we work with radians from day one? Perhaps speaking about pi in school kids makes them wonder. Me?
I know what the thing is.
Okay. Yeah. Suddenly feel much better. The thing is, it's one of the illogical things in our education, because British children were taught about degrees up to the age of 16, and then completely abandoned themselves after 16. We had to do the same thing because British do it, and that's not the best thing to learn. So what we're going to do now is make this mental switch to radians. I hope it doesn't discombobulate you or anything, but that is the unit that we're going to start working with from now. So, when in doubt, just remember what Jeremy said. 2 pi radians is one complete circle, 360 degrees. Good. And therefore, that also means because you measured your angles in degrees using the protractor, using the tonometer, then we now have to convert these to radians. And so you won't have to stay doing that every single time. I've written a short function that does that for you. Now, look at the sentence, please. I'm looking at line 21. Are we all on line 21, either on your laptops or here, please? Now, sorry, let's go on line 22. That's the function that we'll be using more. I've called the function deg2rad, just to remember what it means. It means degrees to radians. But you can just as easily call it, I don't know, Mariana or something. It's just a name. But I gave it a name that that sticks, that reminds me what that function does. Is that clear, please? Now, deg2rad is a function in which I give the computer a quantity called deg, the angle in degrees which I measure. Okay? And here in the curly brackets, we've got the calculation. Degrees times pi, notice that R, like most other computer languages, has the value of pi built in. So you don't have to remember 3.141592654 and all of that, divided by 180. So to convert degrees into radians, because R will only work with radians, there is this function called deg2rad, and the working of that function is obviously function because it's a function. Function means formula, in which we give the computer the value in degrees, and then it works out the degrees times pi divided by 180. This will become clearer when we use it. I'll give you an example of how it works. So I'll just take that line and put it over here. And my version of R now has that function. Now, look what I'm going to do. Let's imagine that, I don't know, Leanne is really curious to know what 30 degrees is in radians. Okay, it's 2 pi on 6 by the way, but anyway, now. So how does it work? We've now defined the function. So to know what 30 degrees is in radians, all right, deg2rad brackets 30. What's not brackets 3, brackets 30. Can you see that? I press that and it's 0.5. It's a bit more than half a radian. Can you see this? I'll just do it again. Katya, where are we stuck?
No, please use it again.
Of course. So in the first step, I defined the function. A function is simply a fancy mathematical name for a formula. Are we okay? Now, in this case, because it's a formula I'll be using many times, I've given it a name. Now, I could give it any name on earth, but I've given it a name which 1 year later helps me remember what the function does. Deg, degrees, to radians. Change degrees to radians. Are we clear about that? Now, so degrees to radians is, that's equals in R. The command is function. I'm telling it that a formula is coming on. Deg means that I'm giving it the value of deg. What I give it is, I'm calling the variable deg. And the working is that number deg multiplied by pi and divided by 180. So I'm doing this now. Julia, your day of birth. Choose a number between 0 and 90. 22. 22? Good. So what I'm doing now is this. Deg to rad, because I'm calling the formula, and then brackets 22, because I'd like to know what 22 degrees is in radians. And it's 0.383974. I mean, your birthday is now 0. Whatever. Are we clear about this, please, all of us? Yes, Crystal and Neve?
So you write functions to find out the function does.
Yes, to define what the formula does. If it's something that I'm just using once, then I don't need to write a function. I just write the formula. If it's a formula I'm going to use many times, like I'm going to use in this case, because I have to calculate the slope at each time, instead of writing the formula each time, I write a function because that will help me. So precisely. Neve? Remember, you don't have to call it deg to rad. You can call it, I don't know, we can call it as usual, our usual go-to variable name, Orchis nivalis, function, I don't know, Dave.
That's because I switched that up. So I did instead that to the.
Oh, don't worry. Okay. Right. I'm going to send all of this. Now, I would rather that you just listen and understand what we're doing, because the actual calculation then is simple. The next thing that I've done, again, we're learning a heck of a lot of R in just a couple of lines here, mainly concepts, is to create a data frame. Now, what's a data frame? A data frame is just a matrix of numbers or letters or something. Are we okay with that, please? But sometimes it has to be declared, defined. Now, look at line 26. Line 26 says this, SLP plot. SLP stands for slope. I'm wondering why I didn't just write slope. Slope underscore plot is a matrix of numbers. That's all. That's all I'm saying over there. Okay? So slope plot is a name, and that's going to be a matrix of numbers. I don't have the numbers yet, but that's going to be a table of numbers. Are we okay with that, please? No, it's what we get from that. But we're going to see how we get that, okay? Now, bear in mind that for many of us, we're taking many steps in R whilst missing the introductory bit. I'm afraid that will often happen. So just take a few things on trust. So in R, if I want to create a table to store the coordinates of the slope that will be my graph, I have to tell it to do that. Remember, you have to explain everything to R to the nearest full stop. Now, by the way, when you were at school, you must have written your exam essays on full stack. Do you remember that? How do you spell full stack? Very good. Many people spell it full stack as though you get half empty stacks or something. It actually stands for full stack. FOOL apostrophe S. You know why? Because in the past, even up to the point when I was still at primary school, it used to be acceptable and even common that the teacher used to ridicule students who were low achievers by making them wear a fool's cap. And the size of paper that could be folded into that sort of conical shape was what we now call a foolscap. Remember, when I was at primary school, it was not uncommon for people to go around in the break with a notice on their back saying, "I am stupid," or something like that. That was seen as being perfectly educational. I never got that on my back. I got beaten up by a pair of hands. It's amazing what they think is education when you fall on the heart yourself. You might be laughing, your mom was in the same school, but she, I don't know if she got beaten up, she was in my sister's class. If I could get beaten up every week, she could do this. Yeah, so that reminds me, foolscap, how did it start talking about that? All right, well, it was interesting. Now, look what we're going to do now. I'm going to set the first two values of this table called slope plot. I'm going to draw it on the board as well, so that you can have some idea. So I've created a table where I'm going to put in my results from where eventually I'll draw the graph that shows us the slope and called it slope plot. In line 26, I've just told our slope plot is a data frame, a table, but it's empty. Now, look at lines 29 and 30. What I'm doing there is filling in the first two values of this table called slope plot. But how does this work? Now, that's the table. And each cell in the table can be identified by a set of coordinates. So, the row number 1, 2, 3, 4, 5, the column number 1, 2, 3, 4, etc. So, if I want to put something in this box, that box would be column 3, row 2. Can you see that? That is its address. Okay, we'll be able to see it. Good. So, what have I started here? I filled in the first values myself. Slope 1, 1. This only has the x and the y. So slope row 1, column 1 is 0. Slope 1, column 2 is also 0. So the way I did that was this: slope plot. Now, square brackets, because that means I'm going to give the address in the matrix. Square brackets, row 1, column 1 equals 0. Do you understand that, please? Oh, yes, sorry. Slope 1, column 2 equals 0. And I've done that to get the whole thing started. Now, I've also got a couple more things here. Realistically, this should be heavily annotated, and the version I'll be giving you will have lots of remarks in it. Now, I've also set a couple of other variables that I'll be needing called y new and x new. And, oh Christ, okay. This now becomes complex here, sorry. Now, what comes next, I'm afraid, is a bit complex. It's something called a loop. A loop is simply a set of commands that you repeat many times. That's all. So, I'm going to try and break it up in this way. What we're doing is that for each of these, we're finding the new x and the new y through trigonometry. So we get the first angle. Now, Kim data was the data that I had here, and Kim data 1, 2, or whatever it is here. Kim data, yeah, would be this. So what we're doing is using these values here to calculate the new x and the new y. I'll do them over here just so that you can see them working. And we'll populate the table step by step manually at first, and then use it doing do that using R. So that's 0, 0. Now, Leanne, do you have the first two coordinates of yours, please? Ten? Okay, 10 meters, and it was 9 degrees, precisely. So what we have is something like this. That's the 10 meters, and that's the 9 degrees. So we need to find the coordinates of that point and then put them in that table. Do you understand this, please? Now, how do we find that? We've got that angle and we've got the hypotenuse. We'll call that y, we'll call that x, because we need to find those coordinates. So that would be xy. And the value of x would be, as you might remember from elementary mathematics, which is not so elementary if you don't remember it, but you know, just revise it a little bit. The value of x is 10 cosine 9 degrees. Now, this is where the problem starts. Because in R, if you write 9 times cosine sine, you get the wrong answer, because R expects angles in radians. Remember that. So as a preliminary step, we change that 9 degrees to radians. Now 22 was 0.5. 9 is about half of that. Let's say 0.25, something like that. 0.2. We change that 9 degrees to radians, so that would be something like 0.2 radians. And 10 times the cosine of 0.2 would give us the new x. It would give us the x coordinate of that point. As regards the height, that would be 10 times the sine of 0.2 radians, and that would give us the y. So the coordinates of this point would now be, I don't know, let's imagine that's 2 and that's 5. Can you get that, please? Yes?
Why they opposites?
Yes, so that's the sine. That's
Okay.
the cosine is adjacent.
Okay.
Now, that's the first one. And so far, that seems simple enough. But we now have to find the coordinates of every other point on the graph. And that's where it becomes a bit more complicated. Because look what we're doing now. We now have to find the coordinates of that point. And the coordinates of that point are found by finding that distance and that distance, but then adding that to that and adding this to this. So if we work out that triangle with an angle of, how much is it? 12. So that's 0.3 radians roughly. If we had to work out that and that, and we get 1 and 2, those aren't our coordinates, because then our graph would look like, basically it goes something like that only. The new coordinate is 2 plus 1, that's 3. 5 plus 2, that's 7. Can you see that? They've got to increase, always, because our graph is going to something like that. Is this understood, please? So, I'll just explain this. We break up the slope into a series of triangles. Did you understand that? For each triangle, we measure the horizontal displacement and the vertical displacement. Is that also understood? If not, don't worry, we'll just explain it. Of course. So, not sure if you remember, Valeria, but when we saw the graph on our first time, the slope looked like something like this. Do you remember this?
Yes. Yes.
Excellent. Now, in order to calculate those, we had to break down each of these into a series of small triangles. Do you remember that?
Mm-hmm.
Great. Now, so that means that to find, or rather to be able to plot the slope on a graph, we need to find each of these coordinates in terms of their x and their y and whatnot. And for the first one, we did that using trigonometry. So way back when we were in Form 3 and wondering why the hell do I need to know sines and cosines and tangents? I don't know why. Yes, Kristen.
But the coordinates, you already know them.
No.
There's a distance.
Because the distance that you have been moving is this distance here, not that distance there. You've been walking up the slope.
But what's the graph? Every point is going to be at 10, 20, 30.
Yes, I thought the y-axis would be the
And
slope,
y.
and the x-axis was going to be the distance.
Because when you were at the park, you weren't walking horizontally, you were walking up the slope.
That's when we plot the graph, that's how we're gonna, just we don't know the actual distance.
That's why we calculate. Because, Kristen, this is the shoreline at Alet Mark. Okay? Now, you moved up 10 meters like that. You agree with that? Great. If we want to plot this on a graph to make it simpler to draw the slope, then that 10 meters is going to be important information. But what we actually really need to know is your horizontal displacement, which was not 10 meters, it was shorter, and your vertical displacement, how far up you went whilst walking 10 meters. Do you understand that? That is why we need to know the up and the horizontal, the X and the Y, using what's its face, trigonometry. Are we okay with this? Are we all okay with this? Great. So, knowing that angle, we can calculate that and that. But what we're going, now this is the key point, please look here. By measuring, sorry, by measuring or by playing about with those triangles, what we're going to get is a set of small distances, small x, small y, small x, small y, small x, small y, small x, small y. And if you plot those on a graph, you'll basically get the same point all over again. To actually plot the slope, we've got to progressively add the x's together and the y's together. So let's do it in this way. Let's imagine that we've got something like this. So we've got, I don't know, Neve's group. You've calculated that, okay, that's 0, 0. We started off from here. That is, that point is now 5, 2, something like that. Now, and we've plotted that on the graph, it's no problem. The second point would be somewhere here. And by working this out, you've calculated that this is, I don't know, 3, 2. Do you understand that? Now, for the first coordinate, 5, 2 can actually be plotted. But if you plot 3, 2 on the graph, so 5, 2 is here, 3, 2 would be somewhere here. So the slope is actually going backwards. You're going to see this. So the real coordinate now is 5 plus 3, that's 8. And 2 plus 2, that's 4. So the graph keeps on going upwards. And you do that for each one of those 10 points that you measured, and you get a real looking graph. And we'll take it down. Right? Now, what I strongly suggest we do is that I'll give you the code properly annotated. Do look through it, please. I can't oblige you. But do look through it. And then we could go through that together. Remember, I mean, I'm doing this because I'd like you to learn how to use that. Because most of my students go to the real world, study abroad, etc., will come back saying, either, why didn't you ever teach us all? Or come back saying, the only thing which I found useful was our whole degree. And that strikes you because you're speaking the language that is spoken universally. I'm not trying to make life difficult. And you don't have to follow this. But if you would, you arm yourself with the tools. Okay? Yes.
Should we start working?
When I send you the code. But try to understand.
So just don't work it on our paper.
If you want to work it out on a rough paper, and you can do that, but John the Baptist have the same thing. I mean, now we've got laptops and we can work it out with ways. But if you have to work it out on a piece of papyrus or something, what did John the Baptist was for Solomon's had to think about? They see what you point
Was actually the daughter's mother or something like that. I don't know.
Well, it's all made up anyway.
Yeah.
Now, let's go back. Yes, Jeremy? How what? Oh, the for loop works like this. So, okay, let me explain it, but this is something that we'll revisit over and over. When you've got a set of commands like a calculation that you need to carry out many times, you don't write it down many times yourself. You just put something called a loop. A loop is simply saying, look, anything from here onwards, repeat 20 times. Now, over here, the way of announcing that you're in a loop is with for, as it is also in BASIC. So for I is just a variable. is from 2 to the number of rows in the data file, Kim data. For each, you calculate the values you had before, and then this is what we did over there, Jeremy. Okay, and then you simply fill it in. This is what you get, etc. So I'd rather go through that with the whole class next week, though. Okay, but that's how you do the loop. Of course, purists in R will probably use a different kind of loop. But I find for loops, even though they're old-fashioned, easy to work with, quite intuitive. But there's other kinds of loops that you can use. And probably, if you put this in ChatGPT and ask it to improve the code, you'll get one of the new kinds of loops. Now, before we stop for today, because I keep on remembering that my friends, the second years, have a lecture now, 2 hours. Shan't come 2 hours. All right. I'd like to show you something that you'll also need for your what's its face, for your site description. For your site description, you'll need to describe the geology and the geomorphology of the area. Now, geology is something chemical. What kinds of rocks do we have there? Now, if you want to know what kinds of rocks there are in the place that we visited, you could either take a wild guess, or else you could do something more sensible. You could use this. So just share screen again. Yeah, I'm going to use this. So if you Google or search for geological map Malta, you get this. You get the geological map of Malta online. You click on that first link, geological map of the Maltese Islands continental shelf. You wait for a few seconds, that's part of the suspense. And then you get into this. And you get lots of blah, 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 and then a map. Then, once again, as you've done 10 trillion times in your life, you click again. And the map now becomes large and becomes active. And what we're going to do now is to zoom into the area that we were, which is over here, Alet Marku. Ma nafx Alet iktar, Alet Marku. Oh, come on. I'm trying to enlarge it to get more detail. It's taking forever to enlarge. Of course, because I'm zoomed out, perhaps. No, all right. Now, this is the Alet Marku Peninsula that we visited. And once the resolution settles down, you can see what we've got here. Now, look carefully. First of all, the Alet Marku Peninsula is pink. The Maltese rock types are color-coded according to their type. You might remember that we've got lower coralline limestone, globigerina, blue clay, green sand, and upper coralline. Well, the lower coralline tends to be pink, but we have different kinds of pink here because we have different kinds of lower coralline. It's like Barbie's party. Now, to know what we've got over here, hover your mouse pointer over the color and click. And If I've enlarged the map too much. Oof, no wonder. So I've just clicked on that color and I've got a pop-up. That color is now highlighted to show me what I've actually clicked on. And it tells me that it's lower coralline limestone. And the type of lower coralline limestone called Schlendi member, because it was first described from Schlendi in Gozo, close enough to Shawkia. But you know, etc. It gives you something about the geological age, description, and whatnot. Then, yes, Steve.
We write Schlendi.
Yes, because it's quite different. Then we go to the other kind of pink, which is a different kind of lower coralline. I think it's a Mara member, I'm not sure. I click on it and it's, no, the Attart member, so that's Nicole. So it's lower coralline limestone, Attart member. You get the Attart member, Schlendi member, Ilmara member, and whatnot. And it gives you a description of it. So to get the surface geology, you use this map. Are we clear about that, please? Now, yes, Neve, you're not interrupting. Yes. But in this case, no, you write Attart member. Yes, but the pink one, the dark pink, then is Attart member. Sorry? Hang on. We're describing the whole of Alet Marco, not just the little corner that you were in. Okay? Yes, I mean, what kinds of rock are there on the site? It's all lower coralline, and half of it is Schlendi member, half of it is Attart member. Now, next thing. Can you see all these lines over here? Do you know what those lines are? They're actually dividing the Schlendi member from the Attart member. Any ideas what those are? They're geological fault lines. Excellent. A fault line is a crack in the rocks. And what would have happened here is that because of one reason or another, the rocks would have split. There's a crack in the rocks. And part of it might have displaced upwards or downwards. So there's a fault over here, which is actually not a very large fault. It goes from Alet Marco to San Paul Tattarja, but it's part of the Great Fault system. And then there's a tiny fault over here where one of the groups was. So what we can say over here is that the surface geology was lower coralline limestone, Schlendi member, and the Attart member, and that the area is cut through by a geological fault. That's something you need to say. You also need to calculate the size of the area. Now, if you're describing the size of the area, its length, breadth, surface area, whatnot, things like that. And you can find these quite easily from a map as well. So I think on Google Drive, I've given you an aerial photograph of the site, but you can easily go on Google Earth. You can easily go on Google Earth, something like this, and you can go on Google Earth, and with Google Earth, you can simply measure the size, the surface area, the length, the breadth of the Alet Marco Peninsula. Are we okay with that, please? All right, so oof. Minu l-qaddis ta' xewkija, Ġulja. San Ġwan, jisniega, jisovja. L-wieħed, daqs kemm hemm San Ġwanijiet, San Ġwan tas-Salib, San Ġwan Battista, San Ġwan Kriżostomu. Alright, dak li tkellimna fuq il-xuttja lil Solomon. Alright, okay. Now, over here, we keep on pinching out to zoom. In fact, it just rotates it. Over here, if you manage to, oh Christ, what am I doing? Call authority, Julia. If you manage what I haven't managed, which is to zoom in on Alet Marku, you can get the coordinates from, you can, it's all right. I mean, you can get them from the map, but what you could also do is use the measuring tool up here. Can you see the toolbar to measure the length, the breadth, and by using the polygon tool, you can measure the area, and so on and so forth. You can use these for anything. So, yes, it's Google Earth. What about it? Do you use it on the website? That's the app. So download the app, and you can